Welcome back, everybody. This is our first video in JEE Mains previous year question series for chapter Nuclei. And before this video, there are several other videos related to other chapters are available on our channel. And you can go to our playlist and find those videos. And if you find these videos helpful, then do press the like button, share them, subscribe to our channel, like to support us, scan the QR codes in front of your screen to donate us any amount. With this, let's start the video. So here the radius of a nucleus of mass number A. Okay, let me adjust pen thickness slightly. Be estimated by the formula R meter. It follows the mass density of nuclear is of the order. So basically what we have to calculate here, we have to calculate the mass density. So we know that mass density is basically mass by volume, and here nothing is mentioned regarding that what atom we have to use. So let us calculate for hydrogen atom. So we will do calculations for hydrogen atom. Now we know hydrogen atom has a one proton plus one electron, and we are only doing for nucleus, means we are only calculating nuclear density. So means electron is a not part of nucleus. So here we have only one proton, so mass will be equal to, that will be equal to 1.67 into 10 raised to power minus 27 kg. Now coming to the volume, and assuming that nucleus is a spherical body, so its volume will be 4 by 3 into pi into radius, and radius of hydrogen nucleus will be just base equal to the using this formula. If we substitute A, that atomic mass is equal to 1, then radius comes out to be for hydrogen nucleus, that will be 1.3 Fermi, or 1.3 into 10 to the power minus 15. So this is 1.3 10 raised to the power minus 15 cube. So when we solve it further, what we will get? We will get 0.181 into 10 raised to the power 18, and that can be written as 1.81 into 10 raised to the power 17. So if we just want to find out the order, that order will be 10 raised to the power 17. That is the option D here. So option D is the right answer. Now let's move to the next one. The ratio of mass density of nuclei of 40 calcium and 16 oxygen. So we know that nuclear mass density is basically constant. So it is equal for hydrogen, for calcium and oxygen also. It is equal for every nucleus. So we can say the density ratio will be 1:1. Now let us move ahead. An unstable heavy nucleus at rest breaks into two nuclei which move away with velocities 8:27, the ratio of their radii. So here our initial unstable heavy nucleus was at rest, and after that those two daughter nuclei move with 8:27 velocity. So let's say velocity v1 is 8x, then velocity of the second will be 27x. Now let us apply momentum conservation here. So initial momentum, because initial nucleus was at rest, so initial momentum is 0, and so final momentum should also be 0. So final momentum will be here equal to, I think masses are not given to us. So let us assume mass of the first one is m1 and mass of the second is m2. So this will be equal to m1 v1 plus m2 v2, and this should be equal to 0. So m1 v1 plus m2 v2 is equal to 0, and from this we can write that m1 v1 is equal to minus m2 v2, and from this m1 by m2 is equal to minus of v2 by v1. So from this minus v2 by v1 will be minus 27 by 8. Now, as we can see here, that this is the mass ratio, and masses are always positive. So what does it mean? That either one of these velocity will be negative. And you can basically, if you know regarding the collision, that initially if nucleus as initial nucleus is at rest, then if due to sudden breakdown or sudden blast, if it splits into two nucleus, then each of these nucleus has to move in opposite direction to conserve the momentum. So means one of the velocity will be negative. So what we can do here, we can just take the modulus, that ratio of masses should be positive, so it will be 27 by 8. So now we have the ratio of masses. Now to calculate the ratio of radiuses, we know that radius is given by r naught times a raised to power 1 by 3, where a is the atomic mass. So r1 by r2 from this can be written as a1 by a2 raised to power 1 by 3. Now ratio of a1 and a2 is basically m1 to m2, and that is 27 by 8. So this will be 27 by 8 raised to power 1 by 3, and this will be equal to 3 by 2. So ratio will be 3 ratio 2. So option C is the right answer here. Now moving ahead, which of the following are the constituents of the nucleus? Now we know that in nucleus, what we have proton plus neutrons. So in nucleus we have proton and neutrons. So that is option B for us. Now if radius of 27 aluminum nucleus is 3.6 Fermi, that of 125 tellurium nucleus will be nearly. So using the formula that R is equal to R naught times A raised to power 1 by 3, what we can write? We can write R1 by R2 will be equal to A1 by A2 raised to power 1 by 3. Now assume first one is aluminium. So radius of aluminium is 3.6 Fermi. So 3.6 by R2 will be equal to A1, that is 27 for aluminium, divided by A2, that will be 125 raised to power 1 by 3. So this will give us 3.6 by R2 is equal to 3 by 5, and from this R2 will be equal to 6 Fermi, and that is option B for us. Now in the next one, you are given that mass of 7 lithium is this value, that of helium and that of hydrogen. When 20 gram of lithium converted into 4 helium by proton capture, energy liberated in kilowatt hour is. Now first of all, what we have to do, we have to write a balanced equation, because masses are mentioned here, that 20 gram of lithium is converted into helium. So we have to write a balance equation first. So what we have? We have 7 3 lithium, and what it's doing? It is doing a proton capture. So it is capturing a proton. So for proton, it will be 1p1, and after capturing a proton, what will it produce? It will produce 8. It is producing helium, so it has to produce 2 moles of helium basically. Only then this equation will be satisfied. So 1 mole of lithium plus we can say 1 mole of protons is producing 2 mole of helium. Now 1 mole of lithium is basically 7 grams. Mass of 1 mole of lithium is 7 grams, and this proton, let us ignore this proton, and okay, its mass is also given. So 1 mole or 7 gram of lithium plus 1 gram of this proton is giving us, that is 8 gram of helium, and that is basically 2 moles. Now it is mentioned that we have 20 gram of lithium. If we have 20 gram of lithium, means we have something, we have around 3 moles. Around 3 moles. of lithium. Why around 3 moles? Not why exactly 3 moles? Because 3 moles of lithium will be equal to 21 gram of lithium. But as per mentioned, we have only 20 gram of lithium. So now we have this equation. Let us find out the Q energy of this equation. Or let's calculate the change in mass. So that delta M here will be equal to the total mass of the parent nuclei, that is 7.0160, plus that of proton, that is 1.0079, minus twice the mass of helium, that is 4.0026. And from this we will get 0.0187 U. So here, as we can see, delta M is positive, means mass of the parent is greater than the uh, mass of daughter nuclei, means mass is lost, and this mass will be lost in the form of energy. So we can calculate that energy will be equal to mc square. So it will be 0.0187, as it is in given atomic mass unit. So what we can do, we can multiply it directly by 931.5, and this answer will be in MeV, mega electron volt. Now I think these answers are given in uh, the answers are given in kilowatt hour, means we need answer in joule basically. So how we can convert it into joule? We can multiply it 0.187 into 931.5 into mega, that is 10 raised to power 6, and it is electron volt, so multiply 1.6 into 10 raised to power 19. Oh, minus charge with minus sign. So when we do this, we will get 2.79 into 10 raised to power minus 12 joule. This is the amount of energy released when 1 mole of lithium, or basically 7 gram of lithium, is converted into helium by proton capture. Now we have 20 gram of lithium, so we can use basically unitary principle. Oh, pardon me that I wrongly quoted this. I quoted that 1 mole is producing this amount of energy. Actually, not 1 mole is producing this amount of energy. It is 1 atom of lithium plus 1 atom of, 1 proton is producing this amount of energy. So 1 atom of lithium, when do a reaction or come in contact with proton, it is producing 2 atom of helium and producing this amount of energy. Now we have 20 gram of lithium. So first of all, what we will do, we will calculate that how what is the number of amount of atoms we have. So we know that 1 mole of lithium is equal to 7 grams. Now in 1 mole of lithium, what we have? In 1 mole we have Avogadro number of atoms. So 6.22 into 10 to the power 3 atoms of lithium equals to 7 gram. Now if we reverse this, that 7 gram of lithium is equal to 6.22 into 10 to the power 3 atoms. Now from this, 1 gram of lithium will be equal to 6.22 divided by 7 into 23 atoms, and as per given we have 20 gram of lithium. So in 20 gram of lithium we have 6.022 into 20 divided by 7 into 10 to the power 23 atoms. So these are the number of atoms we have, and each atom of lithium, when uh, comes in contact with proton, it produces 2.79 or 10 to 12 10 raised to power minus 12 joule of energy. So total amount of energy that is produced here will be basically equal to total E total, that will be 6.022 into 20 divided by 7 into 10 raised to power 23 into 2.79 into 10 raised to power minus 12. This is the total energy, and this comes out to be around 4.8 into 10 raised to power 12 joules. Now we need to convert it into kilowatt hour because answer is in kilowatt hour. We need to calculate energy in kilowatt hour. So let's discuss this kilowatt hour. So kilowatt hour is basically joule of power. Oh, sorry, unit of power, not joule of power. And it is basically number of joule consumed in an hour. So we can derive the value of kilowatt hour from this unit. So let us write that kilo denotes 10 raised to power 3. Watt is basically joule per second, and hour is basically 3600 seconds. So second gets cancelled, and we have answer 3.6 into 10 raised to power 6 joules. So this is our unit. So as per the answer, 1 unit is equal to 3.6 into 10 raised to power 6 joules, and our total energy is 4.8 into 10 raised to power 12 joules. So how many units will be there? So the number of units will be 4.8 into 10 raised to power 12 divided by 3.6 into 10 raised to power 6. So this will give us 4 by 3, basically 1.33 into 10 raised to power 6. So these are the number of units of energy in kilowatt hour which will be produced, and that is option D here. So let me revise the question slightly. Revise the question again, because in starting we might have confused. Might confuse you regarding the discussion regarding the moles concept. So initially we have lithium, proton, and helium, and we know 1 mole of lithium is 7 gram, 1 mole of proton will be basically 1 gram, and 1 mole of helium is 4 grams. So 1 mole of lithium plus 1 mole of proton is producing 2 moles of helium here. And as per the question, we have to find out the energy liberated in kilowatt hours when we consume 21 grams of lithium in the reaction. So when we do the mass calculation, or when we do the delta M calculation, where delta M is the change in mass, so what we do the total mass of the parent minus total mass of the daughter. Now in parent, what we have taken mass of one atom. You keep in mind here that this 7.0160 is the mass of one atom of the lithium. Similarly, 1.0079 is the mass of one proton, and this 4.0026 is the mass of one atom of helium. So that's why when we calculated delta M, it is the mass lost when individual atoms of lithium and proton produces helium. So it is the mass lost by basically when one atom of lithium is entering into reaction. So when one atom of lithium is going into the reaction or entering into the reaction, this is the amount of mass lost. Now from this, then we can convert it into energy. So one atom of lithium is basically producing this amount of energy. Now as mentioned, we have 20 grams of lithium, and in 1 mole of lithium we have 7 grams, and in 1 mole we know there are Avogadro number of atoms. So using that calculation, we can calculate that how many number of atoms there are in 20 grams of lithium, and from that if we multiply those number of atoms with amount of energy produced by one atom, then we get the total energy. Now we have to write this answer in kilowatt hour terms. So we can convert this kilowatt hour into numerical form, that kilo denotes 10 raised to power 3, watt is basically joule per second, and hour is 3600 seconds. So from this we get that 1 kilowatt hour unit is equal to 3.6 into 10 raised to power 6 joules. Now we have to calculate these number of these units into our original energy consumption or overall energy production. That comes out to be 1.33 into 10 raised to power 6. So hopefully this will be clear to you. So with this, let's move to the next one. So given the masses of various atomic particle, proton, neutron, electron, antineutrino, and I think it is deuterium. Yes, D is deuteron. Which of the following process is allowed by momentum and energy conservation? So the basic principle is that for any reaction to happen, for any reaction to happen, and this is only in terms of nucleons or basically nuclear physics. For any reaction to happen in terms of nuclear physics, what we have, we assume that suppose we have some parent nuclei, we have parent nuclei, and there is a reaction happening between the parent nuclei and we are getting daughter nuclei. So what we assume that these daughter nuclei are more stable as compared to parent nuclei. Now, what does this mean if they are more stable? So it means their binding energy per nucleon will be greater. That is basic concept. And how this binding energy per nucleon will be greater? That will be achieved by losing some mass. So we can write that total mass of daughter will be less than total mass of parent nuclei. So that is the basic logic which we are going to apply here. So in the first one we have neutron plus neutron giving to deuterium atom. So here it is mentioned that mass of neutron is 1.0087. So if we add 1.0087 plus 1.0087, this gives us 4, 6, 1, 0 and 2 here. So this is the total mass of parent. So mass of daughter nuclei should be less than this one. So we know that here we have deuterium and mass of deuterium is mentioned to be 2.0141, which is less than the parent. So we can say option A is possible. Now coming to the B, here we have proton giving rise to neutron, electron and antineutrino. Now mass of proton is 1.0072 and giving rise to neutron, where mass of neutron is 1.0087. So we can clearly see here that mass of proton is less than mass of proton, that is 1.0072, that is less than mass of neutron. So here mass of daughter nuclei are greater. So we can say this reaction is not going to be possible here. Now coming to the option C, neutron plus proton giving rise to deuterium plus gamma. Now mass of neutron is again 1.0087 plus mass of proton, that is 1.0072. 1.0072. Now if we add them, we will get, this is the amount number we will get, and this number is greater than mass of deuterium. It is greater than mass of deuterium. So we can say C is also possible from this concept. And now going to the D, that electron plus positron giving rise to gamma. So here it is not mentioned actually what is gamma. So I think this will be a EM radiation, gamma rays. And this is possible because this is basically known as electron, or sorry, not electron, it is known as annihilation process, where electron and positron combine with each other, giving rise to photons. Actually, yes, I forgot to consider one thing, that was momentum conservation. So till now we have applied only energy conservation, and from that energy conservation we can say option A, C and also D is possible from the energy conservation only. Now when these reactions are happening, this electron and positron has to come in contact with each other. So when they are coming in contact with each other, so we can say they will have some initial momenta that should be equal to zero, means sum of their initial momentum should be zero. Now as per the reaction we have only one photon. Now we know that photon also carries a momentum, so this photon will be moving in some direction, let's say in the positive x or negative x direction. So total momentum will not be zero here in case of D. So if total momentum is not zero, we can say option D is not going to be possible here. Now, similarly, if we apply that momentum conservation in case A, that these two neutrons, assuming that initially they are at rest, then we have, means not they are at rest, their total momentum is zero. First one is moving, suppose in positive x, second one is moving in the negative x, they collide with each other and we have deuterium atom. So now this deuterium atom is single one, so momentum conservation is difficult in this case also. So we can say option A is also rejected. So the only possible case which we have, that is neutron plus proton is equal to deuterium plus gamma, where this gamma particle will help us to conserve the momentum. So with this, option C is going to be the right answer here. So hopefully you got the idea that if we apply energy conservation or the basically mass conservation, then option A, option C and option D are allowed. But if we apply momentum conservation, then D is also rejected and A is also rejected. So only left option which is possible, that is option C for us. So with this, let's move to the next one. Find the binding energy per nucleon of 12050 SN. Mass of proton is given, mass of neutron is given, and mass of tin nucleus is also given to us. So binding energy per nucleon can be calculated. First, we have to calculate the total binding energy, or let's calculate the total change in mass, or delta M. So delta M will be equal to here. Mass of neutron is 1.00867. Multiply the total number of neutron, that will be 70 here, plus mass of that is proton, that is 1.000783, into multiply number of proton, that is 50 here, minus mass of the tin nucleus, that is 119.902199. Now from this we will get that mass difference is comes out to be 1.096201 U. This is the mass difference. Now we can convert into energy. So delta E will be equal to delta mc square, and that is in U. So 1.096201 into 931. And from this, what we will get? We will get 1020.56 MeV. Now we have to find out binding energy per nucleon. So what we need to divide it? We need to divide it by the number of nucleons, that is 120 here. So binding energy per nucleon will be equal to 1020.56 divided by 120, and this will lead to 8.50 MeV per nucleon. This is the binding energy per nucleon in this case. Now let's move to the next one. In a reactor, 2 kg of uranium-235 fuel is used up to 30 days. The energy released per fission is 200 MeV. Given that the Avogadro number is this per kilomole and 1 electron volt is this, the power output of reactor is close to. So we have basically burned 2 kg of uranium, and we have to calculate the power output, total power output. So let's start with that. We know that 1 mole of uranium-235 is basically equal to 235 grams. So, or we can say in 235 grams of uranium 235, we have 6.022, or here it is 23, into 10 raised to power 23 atoms. In 235, that is 1 mole, 235 gram of uranium 235 has this number of atoms. So 1 gram of uranium 235 will have 6.023 into 10 raised to power 23 by 235. This is the number of atoms in 1 gram. Now we have 2 kilogram of uranium. So in 2 kilogram, basically we have 2000 grams of uranium. So in 2000 grams of uranium, we have 0.6.023 10 raised to power 23 divided by 235 into 2000. This is the total number of atoms we have. Now let us assume that is the basic assumption here, that what is our assumption? That each U35 atom splits. We are assuming that each of the U35 atom splits, and when each atom splits, it is mentioned that it produces 200 MeV energy. So total energy that will be produced by 2 kilogram of uranium atoms when they split, that will be equal to total number of atoms. These are the total number of atoms which can split, multiply the amount of energy which will be produced after each split, and this is in mega electron volt. So let us convert it into number of joules. So this is the amount of energy in joule which will be get produced in how many days? That will be produced in 30 days. Now our answer is in watts, megawatts. So watt is basically joule per second. So we need answer in joule per second. This energy is in joule. We have the time. So what we need to do? We need to basically divide it by the time to calculate the power. So power will be equal to here. That will be ET by the time. Time is 30 days and ET is this value. So let's substitute 6.0023 10 raised to power 23 2000 into 200 10 raised to power 6 1.6 10 raised to power minus 19 divided by 235, and now divided by the number of days, that is 30 days. Each day have 24 hours, each hour has 60 minutes, and each minute has 60 seconds. So from this, what we will get, the answer comes out to be approximately 62.4 into 10 raised to power 6 watts, and that is approximately 62.4 megawatts. And now if I compare it with the given answer, that is closest to option B. So option B is the right answer here. Now let us move to one more. Let us do one more. Consider the nuclear reaction. Given the binding energy per nucleon are given, identify the correct statement. Which statement is correct? So for this, let's find out that what is the total energy produced here. So delta E, this is the total amount of energy will be either produced or needed for this reaction to be happen. So that will be the difference in the binding energy. So total binding energy of the parent, that will be 20, as it has 20 nucleons, and these numbers are binding energy per nucleon. So 20 into 8.03 minus for the daughter, that will be twice into 4 into 7.07, that is for helium, and for C12 that will be 12 multiply 7.86. So when we solve this, what we will get? We will get 9.72 MeV. So we can see here that this delta E is positive. So basically, if this delta E, which is parent minus daughter, this delta is parent minus daughter. Normally what we do? Normally we do daughter minus parent. So this delta E is positive, and we can also see from this here, from the given values, that binding energy per nucleon of the parent is more as compared to binding energy per nucleon of the daughter nuclei. So basically what we conclude here, that parent is more stable. Parent is more stable than daughter. So if parent is more stable than the daughter, so what we need to do, we have to supply energy. We have to supply energy to do the reaction. This reaction will not happen automatically because parent is more stable. We have to provide the energy to make the parent unstable, and that will then breaks into daughter nuclei. So the amount of energy that needs to be supplied here. So option B and C are straightforwardly rejected, that energy will be released. Here actually energy need to be supplied, and the nearest answer is, that is option D, that is 11.9 MeV is supplied. So option D is the right answer here. So with this we end this video here. Hopefully what we have covered here is again helpful to you. If you find this video helpful, useful, then do press the like button, share it, subscribe to our channel, and want to donate us something, scan the QR code in front of your screen. Thanks for watching, and we will meet in next video.